Imagine staring up into a night sky so vast and silent, it seems infinite, and yet, even on the clearest of nights, the human eye can only perceive a tiny fraction of what's really out there. The universe isn't just stars and darkness, it's teeming with mysteries we've only just begun to unravel. Out there, 300 million light-years from Earth, a breathtaking cosmic drama is unfolding, a place where galaxies don't just drift by one another. They collide, merge, and reshape the very fabric of space and time. Welcome to the Mice Galaxies, one of the most dynamic and chaotic regions of our cosmos. What makes this pair of spiral galaxies so extraordinary isn't just their spectacular dance of destruction and creation. It's what hides within them, objects and anomalies so strange, they defy everything we think we know about how the universe works. We're about to journey into the heart of this celestial collision, where gravity twists spiral arms into long, sweeping tails, giving these galaxies their name, and where forces so powerful reshape entire star systems in real cosmic time. But beyond the sheer visual spectacle lies something even more compelling: 30 bizarre, unexplained objects that astronomers have detected within this turbulent region. These aren't just stars or planets, they're cosmic oddities that challenge our understanding of physics, light, and reality itself. Some of them glow with energies that shouldn't exist. Others vanish and reappear without warning. A few seem to defy the laws of motion as we know them. Each one is a piece of a puzzle that stretches the limits of human imagination. This video is your invitation to step into that mystery. We're not just observing from a distance, we're going to explore these phenomena together, navigating through layers of cosmic wonder and confronting questions that even scientists are struggling to answer. What could be causing these strange readings? Are we looking at black holes behaving in ways we've never seen? Is it dark matter twisting reality right before our eyes? Or could it be something even more extraordinary? Strap in, because we're diving deep into the unknown, where each discovery pulls us further into the beautiful, bewildering weirdness of the universe. This is a journey you won't want to miss, and right at the heart of this cosmic collision, our first strange object sets the tone for everything that follows. Nestled deep within the core of the larger spiral galaxy, known as NGC 4676, is a supermassive black hole. Now, most large galaxies have one of these gravitational behemoths at their center, but this one is anything but ordinary. What makes it so bizarre are the colossal jets of superheated plasma it's firing out into space at nearly the speed of light. Typically, these jets shoot out in a straight line, perpendicular to the black hole's spinning accretion disk, the swirling whirlpool of doomed matter and gas that's falling into it. It's a predictable, well-understood process, but here the jets are anything but straight. They're kinked, twisted, and dramatically misaligned, arcing through the surrounding gas and dust in a wild, chaotic spray of energy that completely defies our standard models. This isn't just a slight miscalculation in angle, it's a fundamental breakdown of the physics we thought governed these cosmic engines. The energy output is staggering, pouring out more power than 1 billion suns, yet it's being sprayed across the cosmos like water from a malfunctioning hose. The leading theory points directly to the galactic merger itself. As these two galaxies entwine, their gravitational fields are creating absolute turmoil, violently shaking the very foundations of the black hole's environment. It's possible that the incoming torrent of gas and stars from the other galaxy is hitting the accretion disk at a strange angle, warping it and forcing the jets to reorient in this erratic, unpredictable way. Another, more exotic idea suggests the merger might have delivered a second, smaller black hole into the system, and now the two are locked in a tight, wobbly dance, their combined gravitational tugs pulling the jets in multiple directions at once. This misalignment is more than just a cosmic curiosity. It's a direct challenge to our understanding of how matter and energy behave under the most extreme conditions imaginable. We're essentially watching a fundamental law of astrophysics being bent and broken in real time, offering us a front-row seat to the chaotic forces that truly shape the universe. It proves that even our most established ideas are just models, and reality, especially in an environment as violent as the Mice Galaxies, is always far more complex and wondrous. But the chaos doesn't end with a single misbehaving black hole. As we pull our gaze away from the turbulent core and out into the long, luminous tidal tails of the galaxy's streamers of stars and gas stretched out by gravitational forces, we find our next cosmic enigma. Drifting through this intergalactic no-man's land is a true gravitational orphan, a colossal star cluster of such immense size and brilliance that it completely redefines what we thought was possible. This isn't your average globular cluster, a common feature orbiting many galaxies. This is a behemoth, a rogue superstar cluster that was likely torn from its galactic home during the violent initial stages of the collision and now wanders alone in the darkness between the two galaxies. What makes this object so strange is its sheer scale. Typical globular clusters are impressive in their own right, containing hundreds of thousands of ancient stars bound tightly together by gravity. But this rogue cluster dwarfs them all, holding millions of stars within its grasp and shining with a luminosity that rivals some small dwarf galaxies. Its estimated age adds another layer to the mystery. While many globular clusters are fossils from the early universe, this object appears significantly younger, suggesting it was born in a more recent, intense burst of star formation, likely triggered by the very galactic collision that then ejected it. Its composition is unusual too, showing an abundance of heavy elements that point to a very active and violent life before it was cast adrift. This celestial wanderer is considered rogue because it is no longer bound to either of the Mice Galaxies. It exists in the gravitational void between them, a sovereign nation of stars on a lonely trajectory through space. Astronomers believe it was flung out from the densely packed spiral arms of one galaxy when the other passed too close, a gravitational slingshot effect of unimaginable power. Its very existence provides a stunningly clear snapshot of the awesome forces at play during a galactic merger. We are literally seeing the pieces that get thrown off the table, and this particular piece is a record-breaking anomaly. It challenges the very classification of star clusters and dwarf galaxies, sitting in a blurry middle ground that forces us to question how such objects form and what ultimately determines their fate. This rogue cluster is a ghost of the collision's past, a brilliant, isolated testament to the violence that can both create and destroy on a cosmic scale. But as we move from the brilliant, star-filled chaos into the deeper darkness between the galaxies, we encounter an object that is, in many ways, the exact opposite of that luminous rogue cluster. It is a presence defined entirely by its absence, a ghost in the cosmic machine. This is our third strange object, and it isn't something we can see with any telescope. Its existence is revealed not by the light it emits, but by the light it bends. Astronomers mapping the Mice Galaxies have observed a small, but incredibly distinct, region where the light from distant background galaxies is being subtly warped and magnified. This phenomenon, known as gravitational lensing, acts like a natural telescope, revealing the presence of a tremendous amount of mass concentrated in that one spot. The sheer force of gravity there is powerful enough to twist the fabric of spacetime itself, but when they point every available instrument at that exact location, scanning for the radio waves of gas, the infrared glow of dust, or the visible light of stars, they find absolutely nothing. It is a void, a perfect massive nothing. This invisible behemoth is a dense clump of pure dark matter, a so-called dark satellite. We believe dark matter makes up about 85% of all the matter in the universe, but it does not interact with light at all. It neither emits nor absorbs it. Its sole interaction is through gravity, and here its gravitational signature is unmistakable and colossal. What makes this particular clump so baffling is its context. During a massive galactic merger where every visible component, stars, gas, dust, is being violently stirred and scattered, we would expect the invisible dark matter to be stirred up as well. Our best models suggest that dark matter, while clumpy, should form a large, diffuse halo around the entire galaxy pair. Finding such a dense, isolated knot of it, completely divorced from any stars or gas, is like finding a solitary, massive iceberg floating in the ocean with no tip showing above the water. It shouldn't be possible under our current understanding. This dark matter clump challenges the very core of our theories about how this mysterious substance behaves, especially during the most dynamic events in the universe. Does dark matter interact with itself in ways we haven't accounted for? Could there be a stickiness or friction within dark matter that allows it to clump together more efficiently than our models predict, even as the visible matter is being torn apart? Its existence as a lone satellite suggests that dark matter might not be as smoothly distributed as we thought, and that these dense, invisible substructures could be far more common than anyone realized. They could be the true scaffolding of the cosmos, the hidden architecture around which visible galaxies are merely assembled. This one invisible knot in the Mice Galaxies forces us to confront the humbling reality that most of the universe's mass is not only invisible to us, but that it operates by rules we are only just beginning to glimpse. It is a silent, gravitational anchor in a sea of visible chaos, and it may hold the key to understanding the true skeleton of our universe. And just as we discover this ghostly knot of dark matter holding its ground, another object demonstrates the incredible power of this collision to not just create, but to violently expel. Imagine a single star not drifting peacefully within its galaxy, but catapulted out into the endless black of intergalactic space at a speed so staggering it defies comprehension. This is our fourth strange object, a hypervelocity star, and it is on a one-way trip to nowhere. Astronomers tracking movements within the Mice Galaxies have pinpointed one such star racing away from the chaotic core at over 2 million miles per hour. At that velocity, you could travel from Earth to the Moon in under 15 minutes. This isn't a gentle nudge, it's a cosmic cannon shot. The most compelling explanation for this incredible acceleration lies in the chaotic dance of the supermassive black holes at the galaxy's centers. As the two galaxies merge, their central black holes are inevitably drawn toward each other, destined to eventually orbit one another in a tight binary system. In this violent gravitational environment, a lone star can wander too close to this dynamic duo. The complex interplay of their immense gravity acts like a slingshot. The star gets caught in their pull, swung around one black hole, and then flung outward by the other with an explosive transfer of energy, an effect known as the Hill's mechanism. It's given a kick so powerful it achieves escape velocity not just from its own solar system, but from the entire galactic system itself. This particular star is a fascinating subject of study. Its composition, analyzed from its light, suggests it was once a resident of the larger galaxy's inner region, a metal-rich environment. Now it's become a solitary traveler, its destiny irrevocably altered. It will never return. It will continue on its trajectory, sailing through the void between galaxies for billions of years, long after the Mice Galaxies have fully merged into a single, new entity. It will become a true intergalactic wanderer, a lonely beacon in an ocean of profound darkness, its light steadily dimming as the vast distances isolate it from any stellar neighbors. The existence of such stars forces us to completely rethink the boundaries of a star's life. We often picture stars living and dying within their home galaxies, but this proves that galaxies can, and do, violently eject their own citizens. This single hypervelocity star is a direct, tangible piece of evidence for the unbelievable forces unleashed during a galactic merger. It's a runaway piece of shrapnel from a cosmic explosion that unfolds over hundreds of millions of years, a perfect example of how the universe can use its most destructive events to create something entirely new and utterly isolated. While the hypervelocity star is a testament to the explosive forces that can eject matter, the collision of the Mice Galaxies is also a powerful engine of creation, forging new structures in the fiery chaos. Our next object is a brilliant example of this creative power, yet it hides its true nature from our eyes. If you were to look at this region through an ordinary optical telescope, you might see little more than a faint, indistinct smudge, easily lost in the spectacular glow of the twin galactic cores and their magnificent tidal tails. But switch your view to the infrared spectrum, and this seemingly dull patch of space erupts into a brilliant, sprawling beacon of light. This is our fifth strange object, a massive, mysterious infrared blob. This enormous, diffuse region is glowing with an incredible intensity in infrared wavelengths, radiating a tremendous amount of thermal energy. The reason it appears so faint in visible light is because it is shrouded in an incredibly thick, dense cocoon of cosmic dust. Think of it like a foggy night. A bright street lamp might appear as a soft, hazy glow because the thick fog scatters and absorbs its visible light. But that same fog would feel warm to the touch because it's absorbing the lamp's energy and re-radiating it as heat, which is infrared radiation. That's precisely what's happening here on a cosmic scale. The energy from a powerful source inside this cloud is being absorbed by the dust, which heats up and subsequently glows brilliantly in the infrared, while the visible light is almost completely blocked. So what is the powerful engine hidden at the heart of this dusty shroud? Astronomers are actively debating two compelling possibilities, and the truth might even be a combination of both. The first theory suggests we are looking at a monumental stellar nursery, one of the most intense and active sites of star birth in the entire galactic system. The colossal shockwaves rippling through the gas and dust of the colliding galaxies have triggered a runaway episode of star formation. Within this blob, thousands upon thousands of new stars could be igniting all at once. The most massive of these infant stars are incredibly bright and hot, bombarding their dusty surroundings with intense ultraviolet radiation. It is this radiation that heats the dust to such extreme temperatures, causing the entire nursery to glow in the infrared like a cosmic Christmas ornament. The second theory proposes an even more violent and spectacular origin. Perhaps the primary energy source isn't a cluster of young stars, but something far more concentrated and energetic, a supermassive black hole flying under the radar. As material funnels toward a black hole, it doesn't just vanish. It forms a superheated accretion disk that can blaze with light across the spectrum. If a black hole were active within this dusty cloud, its accretion disk could be pouring out enough energy to heat the entire surrounding dust envelope to incredible temperatures, creating the infrared blob we observe. The thick dust would then act as a perfect curtain, concealing the brilliant but smaller optical source of the black hole itself, making it appear as a large, smooth glow instead of a pinpoint of light. The existence of this object is a direct and stunning consequence of the galactic collision. The immense pressures and shock waves generated as the two galaxies grind together have compressed vast clouds of gas and dust, either triggering a frenzied burst of star formation or fueling a hidden black hole, or perhaps both simultaneously. Its debated nature makes it a crucial puzzle piece. If it's a stellar nursery, it tells us about the incredible efficiency with which mergers can create new generations of stars. If it's a dust-obscured black hole, it challenges our methods for finding and classifying these gravitational monsters, suggesting that many might be hiding in plain sight, cloaked by their own brilliant debris. This infrared blob is a powerful reminder that the most dramatic processes in the universe often occur behind closed curtains, and to see the true spectacle, we must learn to look in every type of light. While the infrared blob shows us the hidden creative power of cosmic collisions, the very heart of the larger Mice Galaxy, known as NGC 4676a, holds a structural oddity that is just as compelling. This isn't a single, unified core as we might expect. Instead, high-resolution observations from space telescopes reveal that the very center of this galaxy is split, presenting astronomers with a double nucleus. It appears as two distinct, brilliant knots of light nestled extremely close together within the galactic heart, a configuration that immediately signals something extraordinary is happening in this region of extreme gravity. Unraveling the true nature of this double structure required peeling back the layers of light. Astronomers didn't just rely on a single snapshot. They employed a powerful technique known as spectroscopy, which breaks down the light from an object into its individual colors, much like a prism creating a rainbow. By analyzing the specific signatures within the light from each of the two nuclei, they could measure their velocity, how fast each one is moving relative to us. The data revealed something startling. The two nuclei are not stationary. They are whipping around each other at incredible speeds. This rapid motion is the strongest evidence that we are not just looking at a lopsided clump of stars, but rather witnessing a binary dance of incomprehensible power. The leading explanation is that we are seeing two supermassive black holes, each the remnant core of what was once a separate galaxy, now locked in a tight orbital embrace as their parent galaxies merge into one. This discovery is a monumental step in our understanding of how galaxies evolve. For decades, scientists have theorized that when two spiral galaxies like the Mice collide, their central black holes would eventually find each other, sink to the new common center through a process called dynamical friction, and begin to orbit one another. Finding a clear, active binary pair at this stage is like discovering the missing link in the evolutionary chain of galaxies. It provides a rare and precious opportunity to study this phenomenon directly. The distance between them and their orbital speed allow us to estimate their combined mass, which is staggering, and to start a clock on their eventual fate. Over hundreds of millions of years, they will spiral closer and closer together, losing energy through gravitational waves, until they finally coalesce into a single, even more massive black hole in an event that would shake the very fabric of spacetime. However, a minority of scientists propose an alternative, albeit still fascinating, explanation. They suggest the second bright knot might not be a black hole at all, but could instead be a massive cluster of stars that was dragged into the core during the merger. The immense tidal forces pulling the galaxies apart could have wrenched a huge clump of stars from one of the spiral arms and deposited it near the center, where it now orbits the primary black hole, giving the illusion of a dual core. While the velocity measurements make the binary black hole scenario more likely, this alternative reminds us that in the chaos of a merger, even the most central regions of a galaxy can be violently rearranged. Whether it's two gravitational monsters in a dance of death or a tidal debris field of stolen stars, the double nucleus stands as a direct and dramatic signature of the collision, a lasting imprint of the violence required to build the giant elliptical galaxies we see throughout the universe today. Yet another anomaly within the Mice Galaxies pushes the boundaries of known physics even further. This one discovered not by its visible light but by its searing, high-energy scream into the void. Deep within the tangled structure of the smaller galaxy, NGC 4676b, a pinpoint of energy blazes with an intensity that defies all conventional explanation. This is our seventh strange object, an ultra-luminous X-ray source, or ULX. To call it merely bright is a profound understatement. This single object is pouring out more X-ray radiation than 1 million suns emit across their entire spectrum. The sheer power output is staggering, far exceeding the established limit for any known object powered by the accretion of material onto a stellar mass black hole or a neutron star. This isn't just a little brighter, it's in a completely different league of energy, shining with a luminosity that, according to our current models, simply shouldn't be possible. The mystery only deepens when we study its behavior over time. This ULX isn't a steady beacon. It's highly variable, flickering and flaring in its output on timescales that range from hours to months. This variability is a crucial clue. The speed of these changes tells us something vital about the size of the energy-producing engine. Much like a large bonfire takes longer to flare up and die down than a small candle, cosmic objects have a characteristic timescale for variability based on their physical size. The rapid flickering we see here suggests the powerhouse at the center of this maelstrom is remarkably compact, likely no larger than our own solar system. So we are left with a paradox, an object with the energy output of a gigantic phenomenon, but the size of a remarkably small one. Astronomers are actively investigating several compelling theories to solve this puzzle, and each possibility points to an extreme and fascinating astrophysical scenario. The leading candidate is that we have discovered a rare intermediate mass black hole. Our celestial bestiary contains stellar mass black holes, weighing up to several dozen times the mass of our Sun, and the supermassive behemoths that lurk in galactic centers, weighing millions or even billions of solar masses. But the existence of an intermediate class, black holes with masses between 100 and 100,000 suns, has been a long-predicted yet elusive missing link. Such an object would have a deeper gravitational well than a stellar mass black hole, allowing it to accrete matter at a much higher rate and, in turn, release the tremendous amount of energy we observe as X-rays. The violent environment of the galactic merger could have created the perfect conditions for its formation, perhaps through the collision and merger of many smaller black holes or from the collapse of a primordial gas cloud. A second and equally thrilling possibility is that we are not looking at a black hole at all, but at a neutron star that is breaking all the rules. A neutron star is the incredibly dense, city-sized remnant of a massive star's supernova explosion. Matter falling onto its surface is subjected to unimaginable pressure and magnetic fields. Under normal circumstances, there is a strict theoretical ceiling to how bright an accreting neutron star can become, known as the Eddington limit. Beyond this point, the intense radiation pressure from the infalling matter should theoretically blow away any further material, effectively turning off the accretion process. But this ULX is shining far beyond that limit. This suggests the neutron star may possess an unbelievably powerful and complex magnetic field that acts like a funnel, channeling superheated gas directly onto its magnetic poles in two incredibly concentrated, blindingly hot columns. This would allow it to violate the Eddington limit locally, creating these extraordinary beams of X-rays that we see as extreme luminosity. There is even a third, more exotic idea on the table, that we are witnessing a completely new type of accretion phenomenon, one that our current physics cannot yet fully describe. The chaos of the galactic collision could be providing a unique and temporary fuel source, perhaps a dense, continuous stream of gas being fed to a more conventional compact object in a way we've never before observed. The existence of this ULX challenges the very categories we use to classify objects in the universe. It forces us to question our understanding of fundamental limits and processes. Whether it is a missing link black hole, a neutron star defying physics, or something entirely novel, this ultra-luminous enigma is a powerful reminder that the universe is always capable of producing phenomena that push beyond the edges of our current knowledge, shining a brilliant and puzzling light into the darkest corners of astrophysics. While the ultra-luminous X-ray source represents a point of intense, compact energy, our next object is a testament to the immense, sprawling forces that are reshaping the entire system on the grandest of scales. Stretching between the two galaxies like a faint, cosmic umbilical cord is a gargantuan bridge of primordial hydrogen gas. This isn't a delicate filament, it's a vast river of raw material, tens of thousands of light-years long, silently flowing through the intergalactic void. This structure is a direct and spectacular souvenir from the galaxy's first close encounter, a permanent scar from the gravitational violence of their collision. When the two galaxies first swept past each other, their mutual gravity didn't just pull on the stars, it exerted an even stronger pull on the diffuse clouds of gas and dust swirling within them. Stars, while massive, are essentially point-like and often pass by each other without colliding during these events, but gas clouds are enormous and fluid. As the galaxies interacted, their gravitational tides acted like a colossal hand, reaching in and scooping out huge quantities of this gaseous material, flinging it out into the space between them. This process, known as tidal stripping, created this immense streamer, a literal bridge of fuel that still connects the two galaxies millions of years after their initial encounter. The true nature and importance of this structure is completely invisible to optical telescopes. To see it, astronomers must turn to massive radio telescopes like the venerable Very Large Array in New Mexico or the Atacama Large Millimeter Array in Chile. These instruments are tuned to detect the faint radio waves emitted by neutral hydrogen atoms as their electrons change energy states. By meticulously mapping the faint signal across the sky, they can trace the outline, density, and even the velocity of this gargantuan gas stream. The resulting maps reveal a structure of stunning complexity. It's not a smooth, simple ribbon, but a tangled flow, filled with knots, twists, and variations in density that tell the story of its violent birth. This bridge is far more than just a cosmic fossil. It is a reservoir of potential, a frozen promise of future creation. This hydrogen gas is the fundamental building block for new stars. While much of it is now drifting in the relative emptiness of intergalactic space, it is not lost. Gravity is a patient force. Over the next hundreds of millions of years, this gas will slowly begin to fall back toward the newly merged galaxy, or it may collapse under its own gravity in denser regions within the bridge itself. When it does, it will trigger epic waves of star formation, lighting up the darkness with the birth of millions of new suns. This gas bridge ensures that the legacy of this collision is not just destruction, but also an abundance of new life, feeding star formation for eons to come. It is a perfect example of the universe's cycle of renewal, where the very material torn apart in chaos becomes the foundation for the next cosmic generation. But the grand tidal bridge of gas isn't the only structure left behind by the gravitational tides. As we map the stellar populations within the sweeping tails of the Mice Galaxies, a subtle but significant anomaly begins to emerge. Woven into the fabric of the larger tidal stream is a distinct and peculiar grouping of stars that stands out from the rest. Their motion is slightly different, their chemical composition is uniquely primitive, and their distribution tells a story of an ancient tragedy. This is our ninth strange object, and it isn't an object at all in the traditional sense. It is a ghost, the spectral remains of a tiny dwarf galaxy that was utterly consumed by the larger spiral long before the current collision even began. The evidence for this ancient act of galactic cannibalism is written in starlight, but you need a sophisticated instrument to read it. By using spectroscopy to analyze the chemical fingerprints of thousands of individual stars within the tidal tail, astronomers can determine their metallicity, the amount of heavy elements like iron and silicon they contain. Stars that form later in the universe's history, like those in the main spiral arms of the mice, are enriched with these heavy elements which were forged in the furnaces of previous generations of stars. However, this specific group of stars has an extremely low metallicity. They are metal poor, a clear signature of stars that were born in the early, pristine universe, likely in a small, isolated dwarf galaxy that lacked the intense star formation needed to chemically enrich its gas. Their motion confirms their foreign origin. While the majority of stars in the tidal tail are streaming away from the main galaxies in a coherent flow, this group exhibits a slightly different velocity pattern. It's as if you were watching a river and noticed one current of water moving at a subtly different angle and speed. It indicates that this stream of stars came from a separate source and has its own dynamic history. This stellar stream hasn't just been stretched out by the current merger, it was already there, a fossilized remnant from a much older, quieter meal. This discovery profoundly changes the narrative of the Mice Galaxies. We thought we were watching a simple, dramatic dance between two majestic spiral galaxies. But we now see that a third, much smaller partner was involved in this cosmic story eons ago. This dwarf galaxy would have been a faint, insignificant smudge of stars and dark matter orbiting the larger spiral billions of years ago. Slowly, over countless orbits, the immense gravity of the larger galaxy pulled it apart, stretching its stars into a long, thin stream that wrapped around the main galaxy like a faint ribbon long before the second spiral galaxy arrived on the scene. The current collision with the second Mice Galaxy then swept up this pre-existing stellar stream, weaving it into the new, grander tapestry of the tidal tails. Finding this ghostly signature is like an archaeologist discovering a unique piece of pottery embedded in the wall of a much later Roman structure. It tells a story of a culture that existed long before the main event. This ghost of a dwarf galaxy is a direct glimpse into the hierarchical nature of galaxy formation, a process astronomers call galactic cannibalism. It shows us that large galaxies like our own Milky Way were built over time by absorbing countless smaller neighbors. The Mice Galaxies are not just colliding, they are merging atop the ancient ruins of a previous merger, revealing that the history of galaxies is written in layers of destruction and assimilation. This faint stream of ancient stars is a silent witness to that process, a reminder that even in the most chaotic of cosmic events, the ghosts of the past are always present. And now we move from the ghostly remains of ancient galaxies to a force that is entirely invisible, yet whose influence is written across the entire structure of the collision: magnetism. Deep within the swirling chaos of the Mice Galaxies, astronomers have mapped a phenomenon that defies simple expectation. When two galaxies collide, you might predict that their magnetic fields, those invisible architectures of force that guide charged particles, would become tangled, messy, and disordered, lost in the turmoil like strings in a blender. But the reality is precisely the opposite. Measurements reveal that the magnetic fields within the mice, particularly along the sweeping tidal tails and the shock fronts where the galaxies interact, are not chaotic. They are remarkably well-ordered, tightly wound, and dramatically amplified, forming vast, coherent patterns that stretch for tens of thousands of light years. This is our 10th strange object, the anomalous magnetic field structure, a powerful and invisible framework sculpted by the violence of the merger itself. The engine behind this magnetic intensification is the immense shockwave generated as the two galaxies plow into one another. Think of it like this: when a supersonic jet breaks the sound barrier, it creates a powerful shockwave in the air, a region of sudden, extreme pressure and order. The galactic collision is creating a similar effect on a cosmic scale, but instead of air, it's compressing and energizing the diffuse sea of gas, dust, and magnetic fields that permeates the space between stars. These merger shocks race through the galactic material, and as they do, they act like a cosmic comb, brushing the magnetic field lines and aligning them along the direction of the shock front. The process also amplifies the field's strength. By compressing the material, the shocks squeeze the magnetic field lines closer together, significantly boosting their power, much like pressing down on a coiled spring stores and intensifies its energy. We cannot see magnetic fields directly with our telescopes. To map this invisible tapestry, astronomers must rely on a subtle property of light called polarization. As light travels through space, its waves typically vibrate in all directions. However, when that light passes through a region with an ordered magnetic field, dust grains or electrons aligned by that field will preferentially scatter or emit light that is polarized, meaning its waves vibrate primarily in one specific direction. By using specialized instruments on radio and infrared telescopes to detect and measure this polarized light, scientists can essentially trace the orientation and strength of the magnetic fields across the entire galactic system. The resulting maps of the Mice Galaxies show stunningly organized patterns, with magnetic field lines running parallel to the long, elegant tidal tails, as if the entire structure has been meticulously magnetized. This powerful and ordered magnetic environment has profound consequences for the physics of the galaxies. One major effect is on cosmic rays, high-energy protons and atomic nuclei hurtling through space at nearly the speed of light. These magnetic fields act as colossal conduits and traps for these charged particles. The orderly field lines guide the cosmic rays, channeling their motion and preventing them from escaping easily out into intergalactic space. This effectively traps a huge reservoir of high-energy particles within the tidal tails and shock regions, making these areas intensely radioactive and dynamically active. It also means that the magnetic fields can accelerate these particles to even higher energies, effectively turning the galactic tails into powerful and permanent particle accelerators, far larger than anything we could ever hope to build on Earth. Furthermore, these amplified magnetic fields play a crucial and contradictory role in the life cycle of stars. On one hand, magnetic pressure can provide support against the gravitational collapse of a gas cloud, potentially putting a brake on star formation. On the other hand, the fields can also help to channel and funnel flowing gas, increasing its density in specific areas and actually triggering the collapse that leads to the birth of new stars. The presence of these strong, ordered fields adds a complex new layer to the already turbulent environment of the galactic merger, directly influencing where and how the next generation of stars will ignite. This invisible force, shaped by a collision of unimaginable power, is a silent architect directing the flow of energy and the birth of new solar systems in ways we are only just beginning to understand. Nestled within one of the turbulent spiral arms, caught in the gravitational crossfire of the merging galaxies, is a stellar gathering of breathtaking potential and profound fragility. This is a proto-globular cluster, a massive and incredibly young family of stars that represents the very beginnings of what could one day become a permanent, glittering jewel orbiting the merged galaxy. But its future is anything but certain. Observing this object is like watching a fledgling bird perched on the edge of its nest for the very first time. It holds the promise of magnificent flight, but one strong gust of wind could send it tumbling into the abyss. What makes this cluster so remarkable is its sheer scale and youth. It contains the mass of several 100,000 suns, all packed into a region of space that, in cosmic terms, is incredibly dense and compact. Spectroscopic analysis reveals that the stars within it are blazingly hot, brilliant blue giants, the unmistakable signature of a very recent and violent burst of star formation. These are not the ancient, cooler red stars we find in long-established globular clusters. These are stellar infants, perhaps only a few million years old. Their existence is a direct product of the galactic collision, as immense shockwaves compressed gargantuan clouds of gas to the point of catastrophic gravitational collapse, triggering this fireworks display of star birth all at once. Yet, for all its brilliance, this cluster is living on borrowed time. The very forces that created it now threaten to tear it apart. It is not nestled safely in a quiet galactic halo. It is positioned within a dynamic and violently chaotic region, where the gravitational tides from the two circling galaxy cores exert a constant stretching pull. These tidal forces act like a pair of giant, invisible hands, constantly trying to pry the cluster apart. The cluster's own gravity is struggling to hold its stars together against this relentless external pressure. The question of its survival hangs in the balance. If its self-gravity is strong enough, it will manage to hold on to most of its stars, gradually settling into a stable, spherical shape over hundreds of millions of years to become a permanent fixture. But if the tidal forces prove too powerful, they will strip the cluster apart, scattering its stars into the general population of the newly merged galaxy. erasing all evidence of its brief, glorious existence. The fate of this one cluster holds profound implications for our understanding of how the most ancient structures in the universe came to be. The Milky Way is surrounded by over 150 globular clusters, each a dense ball of up to 1 million stars that are among the oldest objects we can observe. For a long time, their origin was a puzzle. How did such massive, coherent structures form so early in the universe's history? The precarious protocluster in the Mice Galaxies offers a compelling clue. It suggests that the intense, compressed environments of galactic mergers provided the perfect crucible for their creation. The violent collisions of the early universe, far more common than they are today, could have produced thousands of these massive young clusters. Many would have been destroyed by the very tides that birthed them, but the ones that formed in just the right place with just the right density would have survived to become the ancient globular clusters we see today. Watching this object is like witnessing a critical moment in cosmic evolution unfold in real time. Its potential dissolution teaches us that galaxy building is a messy, inefficient process, filled with false starts and magnificent creations that are almost immediately destroyed. Its survival, however, would show us the direct link between the most violent events in the universe and the creation of its most stable and enduring structures. This single, brilliant, and unstable cluster is a test case for one of astronomy's oldest questions, and its destiny, whatever it may be, will write a crucial paragraph in the story of how galaxies are assembled. Out in the profound emptiness between the two galaxies, far from the dense stellar nurseries of the spiral arms, lies evidence of a star that lived a solitary life and died a spectacular death in the ultimate isolation. This is our 12th strange object, and it is the ghost of an explosion, an intergalactic supernova remnant. It appears as a faint, expanding shell of energized gas, a perfect bubble of debris slowly growing within the sparse hydrogen of the tidal tail. Finding this object was a triumph of meticulous observation, like spotting a single, fading smoke ring in the vastness of an empty sky long after the firework that created it has vanished. Spotting such a remnant presents a unique set of challenges. Within a galaxy, a supernova remnant often stands out against the complex, bright backdrop of nebulae and star clusters. But here, in the near-total blackness between galaxies, the background is almost perfectly empty. The shell of expanding gas is incredibly faint, its surface brightness pushing the absolute limits of our most powerful telescopes. Its discovery required not a single observation, but a patient campaign of mapping the same region of the tidal tail over many years. Astronomers were looking for a specific signature, a faint, circular patch of gas that was not only glowing with the characteristic light of energized elements like oxygen and sulfur, but was also visibly expanding outward when compared year after year. Confirming its motion was the final, crucial piece of evidence that this was not just a stationary knot of gas, but the evolving aftermath of a titanic stellar detonation. The very existence of this remnant is a profound statement about star formation in the most extreme and unlikely environments. It tells us that within the vast tidal streams of material pulled out during the galactic collision, there were pockets of gas dense enough to collapse under their own gravity and form stars. This was not a large stellar nursery, it was a lonely birth. A single, massive star managed to form in this intergalactic wilderness. It lived its entire life in solitude, burning through its nuclear fuel far from any neighboring stars. And when it could burn no longer, it ended its life in a cataclysmic core collapse supernova, briefly outshining its entire host galaxy fragment before fading away, leaving this beautiful, expanding shell as its only tombstone. Studying this remnant provides a uniquely clean laboratory for understanding the physics of supernova. Within a galaxy, a remnant's expansion and evolution are complicated by its interaction with the complex interstellar medium. It plows into other gas clouds, its shape gets distorted by magnetic fields, and its light gets polluted by the glow of nearby stars. But this intergalactic remnant is expanding into a near-perfect vacuum. Its evolution is pristine, governed only by the initial energy of the explosion and the negligible resistance of the ultra-diffuse gas in the tidal tail. By measuring its rate of expansion and the composition of its shell, astronomers can work backwards with unprecedented accuracy to calculate the exact energy of the explosion and the type of star that died here, gaining pure insights into stellar death that are almost impossible to achieve anywhere else. This lonely bubble of gas is more than just a cosmic curiosity. It is a boundary pusher. It proves that the process of star formation is not confined to the safe, dense cores of galaxies. The violent mechanics of a galactic merger can fling the raw ingredients for stars so far out that they ignite in the void, living and dying in a solitude we can scarcely imagine. This single remnant forces us to expand our definition of where a star can be born and challenges our understanding of the minimum requirements for such an event to occur. It is a testament to the universe's relentless drive to create, even in the most unforgiving and empty of spaces. While we've been focusing on the strange objects born from the collision itself, the immense gravity of the Mice Galaxies also acts as a lens, warping our view of the distant universe and creating a phenomenon of breathtaking beauty and scientific utility. This brings us to our 13th strange object, which isn't an object within the mice at all, but a trick of light, a faint, shimmering arc of bluish light, curved like a smile against the darker backdrop of space. This ethereal arc is a gravitational lens, a natural telescope created by the combined mass of the two colliding galaxies, bending the very fabric of spacetime itself. The light we see in that arc doesn't originate from the mice. It comes from a quasar, an incredibly luminous and active galactic core, located billions of light years behind the mice system. The gravity of the galactic pair acts like a colossal lens, magnifying, distorting, and bending this distant quasar's light around it, creating multiple images and stretching them into this distinctive arc. This cosmic magnifying glass provides astronomers with a powerful two-for-one tool for discovery. Firstly, it offers an unprecedented, high-resolution view of the distant quasar that would otherwise be an impossible-to-study pinpoint of light. The lensing effect can amplify the quasar's brightness by a factor of 10 or even more, allowing telescopes to dissect its structure in fine detail. We can analyze the light from this superheated accretion disk swirling around a supermassive black hole to understand the physics governing these extreme engines at the dawn of the universe. It allows us to study the composition and velocity of gas clouds billions of light years away with a clarity that would be unachievable without this natural assist from the Mice Galaxies' gravity. Secondly, and perhaps more importantly for understanding the mice themselves, the precise shape and brightness of the lensed arc acts as a direct probe of the mass distribution within the galactic pair. The way the light is bent is exquisitely sensitive to the amount and location of all mass in the foreground, not just the visible stars and gas, but the invisible dark matter as well. By meticulously mapping the distortions in the arc, astronomers can create a detailed mass map of the entire mice system. It's like holding a strangely shaped glass lens up to the light. By studying the pattern of the distortions it creates, you can reverse engineer the precise shape and density of the glass itself. This technique has revealed that the dark matter halos of the two galaxies are already significantly overlapping and interacting, providing crucial, real-time data on how this mysterious substance behaves during a colossal merger. The existence of this perfect, aligned lens is a rare and fortunate cosmic coincidence. It requires a near-perfect alignment between a massive foreground object and an extremely distant, bright background source. The fact that we see it here means we are looking at a special sightline, a unique peephole through the universe that allows us to see further and with more precision than we normally could. This lensing arc is a gift from the cosmos, a chance to study two profound mysteries at once: the nature of a monstrously energetic object at the edge of the observable universe, and the hidden distribution of mass, both seen and unseen, in one of the most dynamic collisions closer to home. It transforms the Mice Galaxies from just a subject of study into an active scientific instrument, a natural observatory that helps us unravel the secrets of the entire cosmos. Yet, even as the galactic lens peers outward, a brilliant and peculiar light blooms within the merger itself, a signature of energy so intense it can paint an entire cloud of gas with a single, shocking color. Drifting within the turbulent spiral arms is a vast, ethereal glow, a cloud that shines with an intense and unmistakable greenish hue. This is our 14th strange object, and it belongs to an extremely rare class of phenomena, a smaller-scale version of what astronomers call a green bean galaxy. The name comes from its appearance, but its nature is anything but simple. This isn't a cloud gently reflecting starlight. It is a colossal structure of highly ionized oxygen gas, a region of space where atoms have been violently stripped of their electrons, causing them to emit this specific, brilliant green glow across vast distances. The process that creates this magnificent spectacle is one of the most violent in the universe. For gas to become ionized on such a tremendous scale, it must be bombarded by an incredible flood of high-energy radiation, specifically photons in the ultraviolet range. This is not the gentle warmth of starlight. It is a searing blast that tears matter apart at the atomic level. The sheer size of this glowing cloud immediately tells us that the energy source responsible must be phenomenally powerful and concentrated, like a cosmic flashlight beam so intense it can illuminate a nebula light years across. The most likely candidate for this phenomenal powerhouse is the active galactic nucleus of the larger galaxy, its central supermassive black hole in the midst of a ferocious feeding frenzy. As immense quantities of matter spiral inward toward the black hole's event horizon, they don't just vanish quietly. This material forms an accretion disk, a whirlpool of superheated gas and dust that spins at nearly the speed of light. Friction and immense magnetic fields within this disk heat it to temperatures of millions of degrees, causing it to blaze across the entire electromagnetic spectrum and unleashing a torrent of ultraviolet radiation. This radiation floods out from the galactic core in all directions, and where it strikes vast but relatively quiet clouds of gas elsewhere in the galaxy, it performs a dramatic transformation. The energetic ultraviolet photons smash into the oxygen atoms within the cloud, violently knocking their electrons loose and charging the entire region. When those electrons eventually reunite with the atoms, they release their energy in the form of light, and for doubly ionized oxygen, that light appears as a vivid, glowing green. What makes this particular green bean cloud so fascinating is its location. It isn't centered on the nucleus itself, but is instead situated at some distance within the spiral arm. This tells a dynamic story of motion and change. The active galactic nucleus likely had a period of even more intense activity in the recent past, perhaps triggered by a sudden influx of new gas from the ongoing merger. During that peak of activity, it unleashed a tremendous blast of ionizing radiation. A light echo of that explosion is now washing over this distant gas cloud, lighting it up like a cosmic flare. We are essentially seeing the afterglow of a past outburst, a delayed reaction that allows us to study the history of the black hole's activity. Alternatively, the cloud itself might have been much closer to the core in the past and was then pushed outward to its current location by the immense pressures and shock waves of the galactic collision, carrying its brilliant green signature with it like a fading tattoo. The presence of this object provides a crucial piece of the puzzle regarding how energy from a galactic core can influence and reshape its entire host galaxy. This isn't just a localized phenomenon, it's evidence of the black hole's ability to project its power across tens of thousands of light years, physically and chemically altering the material far from the central chaos. It shows us that the influence of a supermassive black hole is not confined to its immediate vicinity, but can reach out and touch the most remote corners of its galaxy, turning quiet reservoirs of gas into brilliant beacons that signal its immense power. Deep within the swirling disk of the larger Mice Galaxy, astronomers have mapped a river of stars flowing against the cosmic current. This is no ordinary stellar stream. It is a counter-rotating star stream, a vast congregation of stars that orbits the galactic center in the exact opposite direction to the galaxy's primary rotation. It is a cosmic contradiction, a river of suns defiantly moving backwards, and its existence is one of the clearest possible signatures of a galactic merger that occurred billions of years before the current, spectacular collision with the second Mice Galaxy even began. To understand why this is so strange, picture a vast spinning vinyl record. The grooves of the record represent the orderly motion of the galaxy's main disk, with all the stars moving in the same harmonious direction. This counter-rotating stream is like a handful of sand thrown onto the record, but instead of settling into the existing grooves, it somehow manages to spin in the complete opposite direction against the flow. In the stable, isolated life of a spiral galaxy, such a structure is virtually impossible to form naturally. The sheer coherence of this backward-moving stream, holding together against the gravitational pull of the forward-spinning disk, points to only one plausible origin. It is the fossilized remains of a smaller galaxy that was consumed long ago. The story written in this stellar river begins billions of years in the past. A small satellite galaxy, itself containing millions of stars, was caught in the gravitational pull of the larger spiral. Crucially, this dwarf galaxy did not approach from just any angle. Its orbit was retrograde, meaning it was moving in the opposite direction to the rotation of the larger galaxy's disk. As the two systems merged over eons, the immense tidal forces of the larger galaxy began to shred the smaller one apart. But because the victim galaxy was moving backwards, its stars weren't simply absorbed into the general mix. Instead, they were stripped away and deposited into the host galaxy, but they retained much of their original opposite momentum. They were dumped into the disk with a fundamentally different directional signature, like a school of fish suddenly forced to swim upstream in a mighty river. This fossil stream is a gift to galactic archaeologists, acting as a time capsule that allows us to reconstruct a chapter of the galaxy's history that would otherwise be completely erased. By meticulously measuring the velocity, metallicity, and age of the stars within this stream, astronomers can piece together the identity of the galaxy that was consumed. The low metallicity of these stars, for instance, tells us the victim was a small, dwarf galaxy, as such systems lack the multiple generations of star formation needed to create heavy elements. The stream's specific path and density help model the original orbit and size of the devoured galaxy. It provides a stunningly detailed record of a cosmic meal that happened in the deep past, a permanent scar that charts the hierarchical growth of galaxies through cannibalism. The presence of this ancient merger remnant adds a profound new layer of complexity to the current collision we are witnessing. The larger Mice Galaxy was not a pristine, untouched spiral before it met its partner. It was already a hybrid, a product of previous mergers. This means the dynamics of the current collision are even more complex than they first appear, as the internal structure of the galaxy is already laced with the gravitational echoes of its past acquisitions. The counter-rotating stream is a silent witness to this layered history, a testament to the fact that a galaxy's life is a continuous story of destruction and assimilation, where every major event leaves its mark for those who know how to look. Yet amidst this frenzy of creation, where shockwaves are compressing gas into billions of new suns, there exists a profound and puzzling silence. In a vast, dark corner of the smaller galaxy, a monumental cloud of gas and dust hangs in space, a sleeping giant that refuses to wake. This is our 16th strange object, and its mystery lies not in what it is doing, but in what it is not. By all the rules of astrophysics, this colossal nebula, with enough raw material to form tens of thousands of stars, should be a brilliant stellar nursery blazing with the light of newborn suns. Instead, it is a dark, cold, and eerily quiet void within the storm, a cosmic pocket of stillness that defies the very environment it inhabits. The expectation of star formation here is not unfounded. It is based on the clear and overwhelming evidence from across the rest of the merging system. Galactic collisions are the ultimate catalysts for star birth. The immense gravitational tides and powerful shock waves generated as the two galaxies intertwine act like a universal trigger, compressing giant molecular clouds to the point where their own gravity takes over, causing them to collapse into new stars. We see this spectacularly elsewhere in the mice, with regions bursting into light. But this one particular cloud, despite being subjected to the same cosmic forces, remains stubbornly dormant. It is a vast reservoir of potential energy that simply will not convert, a loaded spring that refuses to uncoil. Astronomers are investigating several compelling theories to explain this profound inactivity, and each possibility reveals a different facet of how star formation works, or in this case is suppressed. The first idea revolves around sheer chaos. It is possible that the cloud is caught in a region of such extreme turbulence that the gas within it is too disordered to collapse. Imagine trying to form a snowball in the middle of a hurricane. The wind and motion would tear the flakes apart before they could ever stick together. Similarly, powerful supersonic shockwaves might be ripping through this cloud, stirring up the gas and preventing any single region from becoming dense and stable enough to initiate gravitational collapse. The internal turbulence provides a form of support, a constant buffeting that counteracts the inward pull of gravity. A second and equally fascinating theory points to the power of magnetic fields. We've already seen how the merger has amplified and ordered magnetic fields across the system. It is possible that within this specific cloud, the magnetic field lines are exceptionally strong and are threaded through the gas in a rigid, organized network. These field lines can act like a skeleton, providing structural support against gravitational collapse. For a star to form, gravity must overcome all other supporting forces. If the magnetic pressure inside this cloud is powerful enough, it could be physically holding the gas apart, preventing it from condensing into the dense cores required to ignite new stars. It's a celestial standoff, with magnetism winning the battle against gravity for now. A third possibility is that the cloud is simply waiting for its moment. Star formation might not be an instantaneous process everywhere. This cloud could be in a pre-stellar phase, slowly accumulating mass and increasing its density, building towards a critical threshold. The right trigger, perhaps a particularly strong shock wave from the next close pass of the galaxy cores, or the compression from a nearby supernova explosion, hasn't arrived yet. When it does, this quiet giant could erupt in a sudden, catastrophic burst of star formation, a single epic event that would birth an entire cluster at once. Its current silence would then be merely the calm before an unimaginably powerful storm. The existence of this quiescent cloud is a crucial reminder that the universe is not monolithic in its processes. Even within the most violent and energetic environments, local conditions can create islands of unexpected peace. Studying this object helps us understand the delicate balance of forces that govern star birth. It shows us that having the raw materials is not enough. The environment must be just right for the magic to happen. This sleeping giant challenges the assumption that mergers universally trigger star formation everywhere, revealing a more nuanced and complex reality where creation requires a precise and sometimes elusive set of conditions. And now we turn our attention to a phenomenon that is transient, mysterious, and one of the most energetic events in the modern cosmos. Drifting somewhere within the vast, sweeping tidal tail of the Mice Galaxies, a new kind of signal has been detected, one that defies easy categorization. For a fraction of a second, this point in space erupts, releasing more energy than our Sun will emit over 80 years. And then, just as quickly as it appeared, it vanishes. But unlike the singular flash of a supernova, this event doesn't happen just once. It repeats. This is a repeating fast radio burst, a millisecond duration blast of radio waves that pulses with a strange and unpredictable rhythm, and its location within this galactic collision makes it one of the most compelling mysteries we've encountered yet. The raw power behind an FRB is almost incomprehensible. To generate such an intense, focused burst of radio energy requires conditions far more extreme than a typical stellar explosion. The leading theory points to the most magnetic objects in the universe, magnetars. These are a specific type of neutron star, the collapsed, city-sized cores of dead massive stars, but they possess magnetic fields so powerful they could erase a credit card from halfway across the Milky Way. The thinking is that a starquake on the surface of a magnetar, a sudden cracking of its rigid, neutron-rich crust under immense magnetic stress, could release a cataclysmic shockwave, energizing the surrounding plasma and launching a blistering pulse of radio waves across the universe. The repeating nature suggests this isn't a one-time destruction, but an object enduring ongoing, violent adjustments, perhaps as its incredibly powerful magnetic field slowly twists and recalibrates itself. But the mere presence of a magnetar here is a story in itself, and it's a story written by the galactic collision. Magnetars are the remnants of the most massive, short-lived stars. Their existence implies a very recent and violent burst of star formation, exactly the kind of event the merger of the Mice Galaxies is known to trigger. The colossal shockwaves compressing gas clouds would have spawned a generation of giant stars that lived fast and died young in spectacular supernova, leaving behind these dense magnetic cinders. This FRB isn't just a random event, it's a direct descendant of the merger's creative fury, a natural product of the environment. Its location in the tidal tail is particularly revealing. It means the star that formed this magnetar wasn't born in the serene disk of a stable galaxy. It was born in the chaos, in a stream of gas that was violently ripped out during the galactic encounter and then collapsed to form new stars in the intergalactic wilderness. There are, however, more exotic possibilities on the table. Some scientists speculate that such a precise, repeating signal could be generated by an intermediate mass black hole, that missing link we discussed earlier slowly consuming a companion star. As it strips material from its stellar partner, the gas could form an unstable accretion disk that periodically erupts in coherent bursts of energy. Others have even pondered whether we are seeing evidence of advanced cosmic engineering, though most astronomers consider this the least likely explanation, a hypothesis of last resort when all natural avenues are exhausted. The truth is, the repeating FRB remains an open question, a siren call from the depths of a galactic collision that challenges us to understand the limits of matter and energy. It is a beacon of pure mystery, a reminder that even as we map the grand structure of colliding galaxies, there are still flashes of the unknown waiting to be decoded. Now, within this cosmic laboratory of extremes, we encounter a gravitational paradox that shouldn't exist, a stellar mass black hole that has broken all the rules. In a tight binary system, locked in a dizzying dance with a companion star, this object pulls with the gravity of what was once a star, but its mass is utterly staggering. While typical stellar mass black holes range from about 5 to 20 times the mass of our Sun, this behemoth weighs in at an estimated 50 to 100 solar masses. It is an overmassive stellar mass black hole, a cosmic oxymoron that challenges the very models we use to understand the death of stars. The formation of a black hole is the final, violent act in the life of a truly massive star. When such a star exhausts its nuclear fuel, its core can no longer support its own immense weight, and it collapses catastrophically under its own gravity. However, this process is not perfectly efficient. a significant portion of the star's outer layers is typically blasted away into space in a brilliant supernova explosion. This puts a theoretical upper limit on the mass of the resulting black hole. The progenitor star has to be unbelievably massive to leave behind a remnant heavier than about 40 solar masses, and even then the physics becomes uncertain. The existence of a black hole with 50 to 100 times the mass of our Sun suggests a formation process that circumvented this messy stellar death entirely. One compelling theory for its origin points to the pristine conditions of the early universe. In the cosmic dawn, before the first generations of stars had seeded space with heavy elements, there existed enormous clouds of pure hydrogen and helium. These primordial clouds could have collapsed directly under gravity, skipping the star formation process as we know it, to form what are called direct collapse black holes. These objects would have been born large, with masses ranging from tens to hundreds of thousands of solar masses. However, a smaller, rarer variant of this process could theoretically create a smaller, but still overmassive black hole seed. This particular black hole in the Mice Galaxies could be a relic from that ancient era, a primordial fossil that has survived for billions of years, only now being discovered because it is actively feeding on its companion star and giving away its presence. The other, perhaps more likely explanation is that this black hole is not a first-generation object, but a product of its violent environment. The Mice Galaxies are home to incredibly dense star clusters, both old and new. Within the tight confines of a young, massive globular cluster, stellar encounters are frequent and dramatic. It is possible this black hole began its life as a more typical, massive star that collapsed into a black hole. Over time, in the cosmic pool hall of a dense cluster, it could have gravitationally captured another black hole, and the two merged, creating a larger single entity. This new, more massive black hole would then have a greater chance of capturing and merging with yet another. Through a series of successive mergers in this dense environment, it could have grown to its current, seemingly impossible mass, a patchwork monster stitched together from the remnants of its predecessors. The presence of its binary companion is the key that allows us to weigh it so precisely. By measuring the orbital period and velocity of the visible star as it whips around its unseen partner, astronomers can apply Newton's laws of motion to calculate the mass of the object pulling on it. The result was a figure that defied expectation. This discovery forces a significant revision of our models for stellar evolution and black hole formation, especially in extreme environments. It suggests that the upper mass limit for stellar mass black holes is not a fixed number but is highly dependent on environment. In the chaotic, crowded conditions of a galactic merger, the rules are different and nature finds a way to build giants. This single, overmassive black hole is a direct challenge to textbook astrophysics, proving that even in death, stars can defy our expectations in the most spectacular ways. Yet for all the violence of black holes and the grandeur of galactic tides, some of the most fascinating transformations are happening on a much more intimate scale. Tucked away in a relatively quiet spiral arm, a cosmic partnership is undergoing a drastic and dangerous change. This is a symbiotic star system, a binary pair consisting of a puffy, aging red giant and its dense, Earth-sized companion, a white dwarf. Under normal circumstances, this relationship is a slow, stately dance, but within the turbulent environment of the Mice Galaxies, it has been thrown into a state of chaotic overdrive, creating our 19th strange object, a stellar partnership on the brink of catastrophe. In a typical, peaceful galaxy, the interaction between these two stars follows a predictable, gentle rhythm. The red giant, having exhausted the hydrogen fuel in its core, has expanded to a monstrous size. Its outer layers become so tenuous that its gravitational grip on them weakens. The white dwarf, a former star core made of degenerate matter and possessing immense surface gravity, patiently orbits its large companion. Over millennia, it gently siphons a thin stream of hydrogen-rich gas from the red giant's extended atmosphere. This gas doesn't immediately fall onto the white dwarf. Instead, it first spirals into a flat, spinning disk around it called an accretion disk. The gas in this disk spirals inward slowly, gradually heating up due to friction. Eventually, when it reaches the white dwarf's surface, it accumulates. For a long time, nothing dramatic happens. The hydrogen simply builds up layer upon layer under ever-increasing pressure and heat from the white dwarf below. The extreme environment of the galactic merger has completely shattered this peaceful equilibrium. The same gravitational shock waves and tidal forces that are triggering the birth of new stars are also violently shaking this established binary system. The orbits of the two stars are being perturbed, bringing them periodically closer together than they ever would be in isolation. Furthermore, the external pressure from passing shock waves is actively squeezing the extended atmosphere of the red giant, effectively stomping on it and forcing vast quantities of its material outward toward the waiting white dwarf. The result is a fire hose of fuel instead of a gentle trickle. The accretion disk around the white dwarf is now flooded with gas, becoming denser, hotter, and wildly unstable. This massive and sudden influx of material has pushed the system into a new regime of extreme and unpredictable outbursts. The accumulated hydrogen on the surface of the white dwarf is now being compressed and heated far more rapidly than before. When the base layer of this hydrogen pile reaches a critical temperature of around 20 million degrees Kelvin, it ignites. But this isn't the controlled fusion of a star's core. This is a titanic thermonuclear explosion that tears across the entire surface of the white dwarf in a matter of seconds. The system erupts in a nova outburst, increasing its brightness by a factor of 50,000 to 100,000 in an instant, temporarily outshining all other stars in its local region of the galaxy. Because the accretion rate is now so high, these outbursts are happening with a frequency and ferocity never before observed in such a system. This makes the symbiotic star in the Mice Galaxies a priceless natural laboratory for studying the very latest stages of stellar evolution. We are witnessing, in extreme fast-forward, the processes that can lead to one of the most important phenomena in cosmology, a Type Ia supernova. This specific type of supernova occurs when a white dwarf accrues so much mass from its companion that it is pushed over the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. This is the fundamental stability limit for a white dwarf. Exceed it, and the degenerate matter can no longer support the star's own gravity, leading to a catastrophic collapse and a runaway thermonuclear explosion that completely obliterates the white dwarf. These supernovae are crucial because they all explode with nearly the same peak brightness, making them standard candles for measuring vast distances across the universe. The hyperactive system we're observing is racing toward this fateful limit at an accelerated pace. By studying the intensity and frequency of its smaller nova outbursts and precisely measuring the rate of mass transfer, astronomers can test and refine the models that predict the conditions for a supernova. Is the system actually gaining mass overall, or are the frequent nova explosions ejecting enough material to keep it just below the limit? The chaotic environment of the merger provides a unique opportunity to stress test these theories under the most extreme conditions imaginable. This single, volatile binary system is a miniature preview of a potential stellar apocalypse, offering a front-row seat to the final, dramatic chapter in the life of a star, a chapter that is being written faster and more violently than anywhere else we have ever seen. Out in the profound darkness between the two colliding spirals, a ghost is drifting. This entity, our 20th strange object, is detected not by the light it emits, but by the shadow it casts on the universal radio waves. It is a massive, coherent clump of neutral hydrogen gas, swirling with the distinct rotational motion of a small galaxy. And yet, when astronomers point every optical telescope they have at its location, they find nothing but empty space. There are no stars, there is no stellar light. This is a prime candidate for one of cosmology's most elusive and controversial concepts, a dark galaxy, a structure made almost entirely of dark matter, with the normal matter present only as a wisp of primordial gas. The discovery of this object was a triumph of radio astronomy. Instruments like the Arecibo Observatory and the Very Large Array are tuned to a specific, faint frequency emitted when the single electron of a neutral hydrogen atom flips its spin. By meticulously mapping the intensity and velocity of this 21-centimeter line emission across the sky, astronomers can trace the distribution and motion of this fundamental gas. The map of the Mice Galaxies revealed the expected vast tidal bridge and the disturbed gas within the spirals, but it also showed a small, independent, and incredibly intriguing blob. This blob of gas was rotating as a single, coherent unit, with a velocity pattern that implied the presence of a significant amount of mass holding it together, far more mass than the meager amount of hydrogen gas could account for. The gravity required to keep this spinning cloud from simply flying apart had to be coming from something else, something invisible. This is the heart of the dark galaxy hypothesis. The thinking is that this object is a small, self-gravitating clump dominated by a halo of dark matter. In this scenario, the dark matter provides the gravitational anchor, the immense, unseen mass that gathered the hydrogen gas in the first place and now keeps it spinning in a stable disk. The problem, according to our standard model of galaxy formation, is that where dark matter condenses, it should also pull in ordinary matter. That ordinary matter, in turn, should eventually condense and fragment to form stars. A dark matter halo of this size should be glittering with at least a few million stars. The fact that it isn't, that it appears to be a pure, starless ghost, poses a direct challenge to our understanding of how galaxies are born. The astronomical community is deeply engaged in a fierce and fascinating debate over this object's true nature. One camp argues vehemently that we are indeed looking at a pristine dark galaxy, a rare and precious relic that could fundamentally alter our models. They suggest that for some reason, perhaps because the gas within it was never compressed by a shock wave or a merger, the star formation process never ignited. It remains a fossil from an earlier time, a demonstration that dark matter can form structures that never light up with stars. The opposing camp offers a more conventional, though still complex, explanation. They propose that this is not a stable structure at all, but a temporary tidal dwarf galaxy. During the violent gravitational interaction of the merger, a particularly dense knot of gas could have been spun out into the tail and achieved a temporary gravitational independence. It would be held together by its own gas mass and the ongoing tidal forces, not by a dominant dark matter halo. According to this theory, it might even form stars in the future, or more likely, it will eventually be pulled apart and fade back into the diffuse intergalactic medium. The critical distinction is that a tidal dwarf would contain little to no dark matter, as dark matter, being more spread out in a halo, is not easily captured into these tidal knots like the concentrated gases. The hunt for answers is focused on a desperate search for the faintest glimmer of starlight. Astronomers are using the most sensitive optical telescopes, like the Hubble Space Telescope, to take incredibly long exposures of this precise patch of sky, digging for any sign of stars so old and faint that they were previously missed. The discovery of even a handful of ancient red stars would instantly collapse the dark galaxy hypothesis and solidify the tidal dwarf idea. Conversely, confirming a complete absence of stars down to the deepest possible limits would make the case for a dark galaxy overwhelmingly strong. This object, a seeming void in the cosmos, has become a focal point for a profound question. Are there entire galaxies made of the universe's hidden material, living and evolving in the darkness, forever unseen? The answer, whatever it may be, will force us to rewrite a chapter in the story of how the cosmos builds its structures. At the very heart of the chaos, where the two galactic cores are slowly entwining, lies a pair of monsters on a collision course. We've already identified the telltale signs of the binary supermassive black holes, their dual presence betrayed by the frantic orbital dance of the double nucleus. But this gravitational tango has a final, almost unbelievable act. Current models suggest that when these two behemoths finally spiral inward and merge into one, the event will be so cataclysmic it could fire the resulting single black hole out of its own galaxy like a bullet from a cosmic cannon, an event known as a gravitational wave recoil kick. The physics behind this incredible possibility is both elegant and violent. According to Einstein's theory of general relativity, the merger of two massive objects like black holes doesn't happen symmetrically. As they whip around each other at a significant fraction of the speed of light in their final moments, they emit gravitational waves, ripples in the fabric of space-time itself. These waves carry away immense amounts of energy and momentum from the system. If the merger is perfectly symmetrical, with black holes of identical mass and perfectly aligned spins, these waves are emitted equally in all directions, and the resulting black hole sits neatly at the center of the new galaxy. But nature is rarely so tidy. In the far more likely scenario, the masses are slightly different, and their individual spins are misaligned with their orbit. This asymmetry means the gravitational waves are emitted more strongly in one direction than another. To conserve momentum, the newly merged black hole must recoil in the opposite direction, just like a rifle kicking back into your shoulder after firing a bullet. The power of this kick is almost beyond comprehension. Computer simulations show that under the right conditions of spin and mass imbalance, the recoil velocity could reach several thousand kilometers per second. That is far greater than the escape velocity of even a massive merged galaxy. A black hole weighing millions of times the mass of our Sun could be shot out into the intergalactic void, leaving its host galaxy behind. The evidence for the binary in the mice is the first step on this path. The measured velocities of the two nuclei confirm they are indeed in a tight orbit, and their eventual merger is a virtual certainty on a timeline of hundreds of millions of years. Whether that merger results in a recoil kick depends entirely on the specific properties we cannot yet measure with precision, the exact individual masses, and most critically, the orientation of their spins. The aftermath of such an event would be as bizarre as the ejection itself. The galaxy would be left without its central gravitational anchor. For a time, the stars near the core would continue to orbit the now empty center, held in place by the combined gravity of all the other stars. But over millions of years, the distribution of stars would relax and readjust, potentially creating a new, diffuse core or even a central density that is oddly flat or peaked. The most fascinating consequence, however, would be for any future galactic evolution. A supermassive black hole is thought to play a vital role in regulating star formation by injecting energy into the galactic system through its jets and radiation. With that regulator gone, star formation in the central regions could run wild for a time, or conversely, gas might fail to cool and collapse without the gravitational influence of the black hole. The exiled black hole itself would become a truly lonely giant, sailing through the darkness surrounded only by a faint cloak of stars that were tightly bound to it, a ghost of a core heading into an eternal exile. While we may not live to witness this ultimate cosmic divorce, its possibility reminds us that even the most massive and seemingly permanent structures in the universe are subject to forces of unimaginable power. Yet amid the stellar explosions and gravitational chaos, one of the most delicate and beautiful transformations is occurring on a microscopic scale. Within a vast, glowing nebula situated along the leading edge of the galactic collision, astronomers have discovered a region where the very dust of the cosmos has been fundamentally altered. This isn't just any dust, this is dust that has been forged and refined in a cosmic furnace, taking on a structure that is eerily familiar. spectroscopic analysis has revealed that the silicate dust grains here have a startlingly high fraction of crystalline structure. To put it in simpler terms, a significant portion of this cosmic dust isn't amorphous and chaotic. It is ordered, structured, and essentially microscopic crystals. This is the signature of minerals like forsterite and enstatite, the very same building blocks that make up gems like peridot and many types of sand on Earth. We are looking at a cosmic gem factory operating on an unimaginable scale. This discovery is baffling because of the specific conditions required to create this crystalline structure. In the cold, quiet depths of normal interstellar space, silicate dust is almost entirely amorphous. The atoms of silicon and oxygen are jumbled together in a chaotic, glass-like state, much like the structure of obsidian. For this dust to reorganize itself into a neat, repeating crystalline pattern, it requires a tremendous and sudden influx of energy, a sharp, intense thermal shock that heats the grains to just the right temperature, somewhere between 1000 and 1500 degrees Kelvin for a very specific amount of time. It's a process called thermal annealing. If the heat is too little or too brief, nothing happens. If it's too much or too long, the dust grains will simply be vaporized back into their constituent gas. This process requires a delicate Goldilocks-style event that is not common in the typical life of a galaxy. The violent merger of the Mice Galaxies provides the perfect, if brutal, mechanism for this transformation. The leading theory points directly to the colossal shock waves that are continuously rippling through the system. As the two galaxies plow through each other, they generate supersonic waves of compressed gas and energy that race outward at millions of miles per hour. When one of these shock waves slams into a relatively calm, dusty nebula, it acts like a sudden, overwhelming blast from a cosmic forge. The event is incredibly violent but also incredibly brief. The dust grains are flash heated to the precise temperatures needed for crystallization in a matter of hours or days, and then they are rapidly cooled by the expanding, thinning gas behind the shock front, effectively freezing them in their new crystalline form. This process is so efficient that it can convert a significant fraction of a nebula's dust content almost instantly on astronomical timescales. There is another, even more spectacular possibility. The energy required for this transformation might not be coming from a broad shockwave, but from a single, pinpoint source, a supernova explosion occurring right inside the dusty cloud. The unimaginable flash of ultraviolet and X-ray radiation from a nearby stellar death could provide the intense, sudden pulse of heat needed to anneal the dust in a spherical shell around the explosion. The fact that this crystalline dust is found in a specific, concentrated region supports the idea of a localized event, whether it's a recent supernova remnant or the focused shock from a particularly strong interaction between colliding gas clouds. This isn't a gentle process. It is the universe's way of taking its raw, chaotic materials and, through a moment of extreme violence, imposing a beautiful and ordered structure upon them. The implications of this crystalline dust extend far beyond the Mice Galaxies. Our own solar system formed from a cloud of gas and dust that was likely enriched by the ejector of earlier supernova and the shock waves from passing stellar events. Meteorites that fall to Earth today contain within them tiny, ancient grains of crystalline silicate stardust that was forged in these same kinds of events billions of years ago. The discovery of this active gem factory in the mice provides a living, observable model for how the very ingredients that went into forming our planets and even the sand on our beaches were first created. It directly links the most catastrophic events in the galaxy to the creation of the smallest, most ordered structures, proving that destruction and creation are two sides of the same cosmic coin, and that even in chaos there can be a breathtaking and delicate order. Now let's pull our focus outward to the very tip of one of those magnificent, sweeping tidal tails. There, shimmering against the blackness of intergalactic space, is a knot of brilliant light, a chaotic swirl of young, blue stars enshrouded in the pinkish glow of ionized hydrogen. This isn't just another star-forming region. This is something far more ambitious. This is a proto-galaxy in the flesh, a structure with the audacity to try and become a galaxy itself. We are witnessing the potential birth of a tidal dwarf galaxy, an object forged entirely from the debris of destruction, now attempting to build something new and independent. This celestial fledgling was born from pure chaos. When the two spiral galaxies made their first close pass, their gravitational tides didn't just pull gently, they acted like colossal hands, reaching deep into their galactic disks and violently flinging out massive streams of gas, dust, and whatever stars were caught in the turmoil. The material at the very leading tip of this ejected tail experienced the most extreme forces, traveling the farthest and fastest. As this torrent of gas raced into the void, it began to cool and fragment. Local pockets of higher density started to collapse under their own gravity, igniting the furious burst of star formation we now see lighting up the darkness. This object is, in the most literal sense, a piece of a galaxy that was torn off and is now trying to make it on its own. The critical question, the astronomical cliffhanger, is whether this glittering knot has what it takes to survive. For it to become a true, stable, gravitationally bound dwarf galaxy, it must win a fierce battle against two powerful foes. The first is its own internal kinetic energy, the frantic, random motion of the gas clouds and newly formed stars within it. This chaotic energy acts like a pressure, constantly trying to blow the cloud apart. The second, and perhaps more formidable foe, is the relentless pull of tidal forces from the massive merged galaxy it is fleeing from. Even at this great distance, that gravitational pull is immense, constantly stretching the proto-galaxy, trying to pull it back in or tear it into streamers. The outcome of this battle boils down to a simple yet profound calculation of mass and density. Astronomers are using the light from its young stars and the radio emissions from its gas to take a celestial census, adding up the total amount of material gathered here. They are looking for a specific threshold. Does the combined gravitational pull of all this mass, the stars, the gas, and crucially, any dark matter that might be present, overcome the disruptive forces trying to tear it apart? If the answer is yes, this object will eventually settle into a stable, orbiting dwarf galaxy. It will become a permanent, albeit small, satellite of the giant elliptical galaxy that the mice will eventually become, a living testament to its violent origin. But there's a fascinating and pivotal twist in this story. Unlike all other galaxies, a tidal dwarf galaxy might be unique in what it's made of. When the tidal forces ripped this material from the outer disks of the spiral galaxies, they primarily grabbed the gas and stars that were there. This is a crucial distinction because the outer disks of galaxies are believed to contain very little dark matter, which is thought to reside in a large, diffuse halo surrounding the visible galaxy. If this tidal dwarf is built only from the visible, ordinary matter stars and gas that was stripped away, its gravity might not be strong enough to ultimately hold itself together against the tidal forces. It could be doomed from the start, destined to slowly dissipate over hundreds of millions of years, its stars scattering into the intergalactic medium as a faint stream. However, if observations eventually confirm that this object is stable and contains far more mass than its visible light suggests, it would upend our understanding. It would imply that the tidal forces were somehow able to pull a significant amount of dark matter out of the halo and bind it into this new structure, a process our current models find very difficult to explain. So we are left watching this cosmic experiment unfold. The future of this object is a direct test of our theories of gravity, dark matter, and galactic evolution. It is a candidate for a new world, born from the ruins of the old, fighting for its right to exist in a universe that is often indifferent to such struggles. Its success or failure will write a key paragraph in the manual of how galaxies are born, live, and die. tucked away in a remote and ancient globular cluster orbiting the Mice pair, a solitary star burns with a light so pure it seems almost primordial. Spectroscopic analysis reveals a signature that sent shockwaves through the astronomical community. This star possesses virtually no metals. In astronomical terms, metals refer to any element heavier than hydrogen and helium. This star's atmosphere is more than 1,000,000 times poorer in these heavy elements than our own Sun. It is a composition that should not exist in the modern universe, a chemical fossil that points to one incredible possibility. We may be looking at a relic from the dawn of time, a candidate for a population 3 star. The very concept of population 3 stars has long been a theoretical cornerstone of cosmology. These would be the universe's very first stars, forged from the pristine hydrogen and helium that emerged from the Big Bang. Without any heavier elements to help cool the gas clouds and facilitate fragmentation, these firstborns are believed to have been monstrous behemoths, hundreds of times more massive than our Sun. They would have lived ferociously short lives, burning through their nuclear fuel in only a few million years before exploding in cataclysmic hypernova. These titanic explosions would have seeded the cosmos for the very first time with the heavy elements, the carbon, oxygen, iron, and silicon, that would go on to form all subsequent generations of stars, planets, and life itself. Because of their brief lives, population 3 stars were thought to have vanished billions of years ago, their existence inferred only by their impact on the chemical evolution of the cosmos. Finding one still shining today would be like finding a living dinosaur. This is why the candidate star in the Mice Galaxies is so profoundly baffling and thrilling. Its existence challenges the entire timeline of stellar evolution. How could such a pristine object survive for over 13 billion years? The prevailing theory is that this star might not be a true monolithic population 3 giant, but a rare and tiny descendant. Perhaps it formed from a small, miraculously unpolluted pocket of gas that survived unchanged since the early universe, only collapsing into a star relatively recently. Even that scenario is incredibly unlikely, as the universe has been thoroughly mixed and enriched by supernova for eons. Another, more dynamic possibility is that this star was born in a tiny, isolated dwarf galaxy that itself formed very early on and through sheer luck never experienced significant star formation or pollution. This dwarf galaxy would have then been captured by the larger Mice Galaxy during an ancient merger, preserving its stellar fossil within its cluster until the present day. The chaotic environment of the ongoing Mice merger is perhaps the only place such a relic could be found and studied. Galactic collisions are the ultimate archivists and excavators. They can rip apart ancient dwarf galaxy companions, scattering their stars into streams and clusters, making previously hidden and rare objects suddenly visible against the brighter backdrop of the main galaxies. The same gravitational turmoil that creates new stars also has the power to unveil the oldest ones. The intense scrutiny this system is under, using the world's most powerful telescopes, provides the deep, high-resolution spectroscopy needed to even detect such an unusual chemical signature. Confirming this star's status is immensely difficult. Astronomers must painstakingly rule out every other possibility, such as it being a previously known, extremely metal-poor population 2 star, or whether its strange light is caused by some unusual atmospheric effect. The hunt is on to find more stars like it in the same cluster to see if they share this pristine composition. If confirmed, this anachronistic star would be one of the most significant discoveries in modern astronomy. It would provide our first direct window into the conditions of the very early universe, allowing us to study the pristine material from which everything we see was ultimately built. Its internal structure and lifespan would offer critical data to test our models of how those first monstrous stars lived and died. This single, faint point of light in a colliding galaxy is a potential time machine, a messenger from the cosmic dark ages that could finally illuminate the story of how our universe went from a simple, empty expanse of hydrogen and helium to the complex and beautiful cosmos we inhabit today. And now we turn to a phenomenon that is not just seen or heard, but felt in the very fabric of reality itself. The orbital dance of the two supermassive black holes at the heart of this collision is doing more than just reshaping their immediate surroundings. They are rhythmically pounding on the universe, sending out faint, persistent ripples in the structure of spacetime. These ripples are gravitational waves, and the signal from this binary pair is a key contributor to what astronomers call the stochastic gravitational wave background, a low cosmic hum that permeates the entire cosmos, the combined whisper of every massive, circling object in the universe. To understand this, imagine the universe not as a silent vacuum, but as a vast celestial ocean. The merging of two stellar mass black holes might be a single, loud splash, a distinct gravitational wave event that our current observatories like LIGO and Virgo can pick up as a clear chirp. But the supermassive black hole binary in the Mice Galaxies is something entirely different. It's more like a relentless, rhythmic drumbeat. These black holes are so immensely heavy, weighing in at hundreds of millions of solar masses, that their orbital motion is relatively slow and stable. They complete a single orbit not in seconds but over a period of years. This creates a gravitational wave signal that is not a transient chirp, but a continuous monochromatic tone, emitting waves at a very specific, low frequency determined by their orbital period. The frequency of the waves they produce is crucial and places them in a band that is currently just out of reach for our ground-based detectors. LIGO and Virgo are exquisitely tuned to catch the high-frequency waves from the final, frantic moments of stellar mass mergers. The low, steady drone from a system like the one in the Mice falls into the nanohertz frequency range. Detecting this requires a telescope of literally astronomical proportions, one that uses the entire galaxy itself. This is the goal of pulsar timing arrays, incredible projects that use nature's most precise clocks, millisecond pulsars. These are rapidly spinning neutron stars that sweep beams of radio waves across the sky with a timing consistency that rivals atomic clocks. By monitoring a network of these pulsars across the Milky Way for decades, scientists look for minuscule, correlated distortions in their ticking. These tiny timing anomalies are the telltale sign of a nanohertz gravitational wave stretching and squeezing the space between us and the pulsar as it passes by. The significance of detecting this specific hum from the Mice system, and others like it, cannot be overstated. It would open an entirely new window onto the universe, allowing us to census the population of supermassive black hole binaries. This would answer fundamental questions about how often galaxies merge and whether their central black holes inevitably find each other and coalesce as our models predict. Furthermore, the exact properties of the wave, its amplitude and frequency, would allow us to precisely weigh the black holes and measure their distance from us, providing a powerful new tool for cosmic cartography. But perhaps most profoundly, the stochastic background is the combined sound of all these binaries across cosmic history. Listening to it is like hearing the universe's ongoing growth, a deep, resonant chord played by the gravitational engines at the heart of every galaxy that has ever merged. It is the sound of cosmic structure being built, and the binary in the Mice is adding its own powerful note to that eternal chorus. But the chaos of the collision doesn't just throw material out into the tails, it can also sculpt it into structures of stunning and improbable geometry. Orbiting the main body of the larger galaxy, like a belt around its waist, is a vast and luminous ring of stars, gas, and dust. This is no ordinary feature. It is a polar ring, a structure that defies the conventional flat disk of a spiral galaxy by circling around its poles, perpendicular to the main plane. It's as if someone took a second, smaller galaxy, twisted it 90 degrees and wrapped it around the first, and in a very real sense, that's precisely what happened during the violent gravitational interaction of the merger. This magnificent ring is a fossilized record of the collision's precise trajectory and timing. When the smaller galaxy made its first close pass by the larger one, it didn't just fly by. It plunged through the larger galaxy's disk at a steep, inclined angle. As it did so, its own gravity reached out and snatched a colossal stream of stars and gas from the larger galaxy's outskirts. But because of the specific angle of impact, this material wasn't flung out into a tail. Instead, it was whipped up and over the poles of the larger galaxy. The stolen material was given so much energy and angular momentum that it couldn't fall back into the main disk. Instead, it settled into a stable, independent orbit that circles the galaxy at a right angle to everything else, a permanent monument to that first catastrophic encounter. The material within this ring is now on a long and slow journey of evolution, a celestial ballet that will unfold over billions of years. Initially, the ring is a dynamic and chaotic place. The gas within it, now compressed and shocked by its new orbit, is igniting with a frenzy of new star formation, lighting up the structure in brilliant blue clusters and pink nebulae. But this vibrant activity is temporary. Over eons, the ring will begin to feel the subtle but relentless effects of dynamical friction and gravitational interactions with the main galactic disk. The same forces that created it will now work to dissolve it. The ring's perfect circular orbit will gradually destabilize, warping and wobbling. The gas and stars within it will start to spread out, their paths becoming more diffuse and disordered. Eventually, the distinct ring structure will blur and fade, its material slowly raining down onto the main galactic body or being scattered into the galactic halo. This process is not a destruction but a transformation. The metals forged in the ring's short-lived massive stars will enrich the larger galaxy's gas reservoir. The kinetic energy of the infalling material will stir up the galactic disk, potentially triggering new waves of star formation. The polar ring, a temporary and glorious structure born from a single, violent event, will ultimately be absorbed, its existence ending not with a bang, but by seamlessly weaving itself back into the fabric of the galaxy it once orbited. It is a brilliant, fleeting chapter in the billion-year story of this merger, a perfect demonstration of how the universe uses chaos to create breathtaking order, if only for a little while. Stretching far beyond the visible boundaries of the colliding galaxies, into the profound emptiness that separates them from their cosmic neighbors, lies an emission of energy so faint and vast it was only revealed by years of painstaking observation. This is not a structure of stars or gas, but a ribbon of pure, high-energy power, a filament of gamma-ray light that seems to tenuously connect the Mice Galaxies to the larger cosmos. Discovered by the incredibly sensitive Fermi Gamma-Ray Space Telescope, this object is a testament to the fact that the influence of a galactic merger does not stop at the edge of the visible tidal tails. It can project its power across millions of light years, effectively weaving the event into the invisible fabric of the universe itself. Gamma rays represent the most energetic form of light in the universe, typically produced by the most violent and extreme processes imaginable. To produce a sustained, large-scale glow in this part of the spectrum requires a continuous source of immense power and a mechanism to convert that power into light. The leading theory points directly to the merger as the ultimate engine, the colossal shockwaves rippling through the system at thousands of kilometers per second act as nature's most powerful particle accelerators. These shocks grab hold of protons and atomic nuclei, the constituents of cosmic rays, and whip them up to velocities infinitesimally close to the speed of light, imbuing them with staggering amounts of energy. Once accelerated, these ultra-high-energy cosmic rays do not stay confined to the chaos of the merger. They escape. They stream out along the faint magnetic field lines that have been stretched and ordered by the merger shocks, fleeing into the intergalactic medium, the sparse, primordial gas that faintly permeates the vast voids between galaxies. This medium is not a perfect vacuum. It contains a few hydrogen atoms per cubic meter, For a proton traveling at near light speed, this thin gas is like a dense fog. As these runaway cosmic rays collide with the protons and electrons within this intergalactic gas, the interactions are violently energetic. They produce neutral pions, subatomic particles that almost instantly decay into pairs of gamma-ray photons. It is this faint secondary glow from countless trillions of these interactions across a volume of space that could contain thousands of galaxies that we detect as the extended filament. This transforms our understanding of the merger's impact. We are no longer just looking at a local event reshaping two galaxies. We are witnessing a form of cosmic feedback on a truly colossal scale. The merger is actively polluting the intergalactic medium for millions of light years around it, injecting it with a vast reservoir of high-energy particles and radiation. This has profound, long-term consequences for the future evolution of this entire region of space. The energy deposited by these cosmic rays can subtly heat the intergalactic gas, raising its temperature and making it more difficult for it to later collapse under gravity to form new galaxies. It's a process that can suppress future star formation on a scale far larger than the merger itself, effectively regulating the growth of structures across a vast cosmic volume. The gamma-ray filament is a direct and observable link between the specific, violent event of the Mice collision and the overarching ecosystem of the cosmic web. It shows us that galaxies are not isolated islands. They are dynamic engines that communicate with their surroundings through energetic outflows and particle winds, seeding the voids with the echoes of their most powerful explosions. This faint, high-energy bridge is a permanent signature of the merger's power, an invisible monument to its role in shaping not just its own destiny, but the thermodynamic future of its entire corner of the universe. Now imagine a vast field of distant stars shining behind the turbulent chaos of the Mice Galaxies. Most of the time, their light is steady and constant, but every so often something incredible happens. One of these background stars will, without warning, suddenly flare in brightness, becoming dramatically more luminous over a period of days or weeks, only to slowly fade back to its original state just as mysteriously. This isn't a star undergoing some internal change. It is the signature of an invisible object drifting through the foreground of the Mice system, its gravity acting as a momentary magnifying glass. These are microlensing events, and they provide us with a powerful and completely unique way to take a census of the countless dark, compact objects that would otherwise forever remain hidden from our view. The principle behind this cosmic trick of light is a small-scale version of the gravitational lensing we see on a galactic scale, but it relies on the precise alignment of just three objects: a distant background star, a closer, compact lensing object within the Mice Galaxies, and our telescope here on Earth. According to Einstein's theory of general relativity, mass warps the fabric of spacetime. When a compact but massive object, like a black hole, a neutron star, a white dwarf, or even a rogue planet passes directly between us and a far more distant star, its gravitational field bends and focuses the light rays from that background source. From our perspective, this focusing effect acts like a natural telescope lens, causing the star to temporarily appear dozens or even hundreds of times brighter than it normally would. The specific characteristics of each brightening event are a treasure trove of information. The duration of the flare tells us the mass of the invisible lensing object. A Jupiter-sized rogue planet might cause a brightening that lasts only a few hours or days, while the lensing effect of a stellar mass black hole could stretch on for several months. The shape of the light curve, how sharply the brightness rises and how symmetrically it falls, gives us clues about the lens's trajectory and whether it might itself have a companion, like a planet orbiting a neutron star. Most crucially, the maximum amplification of the light directly reveals the mass of the object causing the lensing. This allows astronomers to literally weigh these dark entities solely through their gravitational influence, with no need to see them directly. This technique is the only way we have of detecting the vast population of isolated compact objects roaming the Mice Galaxies. For every star that ends its life in a supernova and leaves behind a neutron star or black hole, many are likely flung out of their birth systems by the violent recoil of the explosion, becoming solitary wanderers in the galactic dark. Similarly, the gravitational turmoil of the merger itself can strip planets from their parent stars, creating a sea of rogue worlds adrift between the stars. These objects emit little to no light, making them virtually impossible to find by traditional means. But through microlensing, their presence is revealed by the subtle, temporary fingerprints they leave on the light of others. By statistically analyzing the rate, duration, and intensity of these microlensing events, astronomers can build a demographic profile of this dark population. They can estimate how many stellar mass black holes are drifting through the galactic halos, determine the abundance of neutron stars, and even get a count of the trillions of rogue planets that were ejected from their solar systems during the chaotic dance of the merger. Each flash in the darkness is a data point, a single measurement in a vast survey of the unseen. This invisible architecture of compact objects makes up a significant portion of the total mass of the galaxies, and until now, it was a complete blank in our models. Microlensing events are finally allowing us to fill in that blank, revealing the true, full weight of the Mice Galaxies, not just the part that shines. Deep within the tangled spiral arms, a star is dying in a spectacular and strangely beautiful way, painting its surroundings with the soot of its own demise. This is no ordinary aging star. It is a carbon star of phenomenal luminosity, a bloated crimson giant that has become one of the brightest infrared beacons in the entire galactic system. Its visible light is a dim, deep red, but when we shift our view to the infrared spectrum, it erupts into an astonishingly brilliant object, outshining entire star clusters. This incredible glow doesn't come from the star's surface itself, but from a vast shroud of its own creation, a colossal shell of carbon-rich dust that it is steadily ejecting into space, a cosmic chimney billowing smoke into the galactic winds. The life of a star like this is a story of elemental alchemy. It began its life as a relatively ordinary star, not too different from our own sun, but with a bit more mass. For billions of years, it fused hydrogen into helium in its core, shining steadily. As it aged and exhausted this fuel, its internal structure changed dramatically. The core began to contract and heat up, eventually becoming hot enough to begin fusing helium into carbon. Meanwhile, the outer layers of the star expanded outward, cooling and turning the star into a vast, cool red giant. In most stars, this is where the process would stall. Oxygen in the star's outer layers would typically bond with the carbon being produced, forming carbon monoxide gas and locking away the carbon. But in this particular star, the ratio of carbon to oxygen has tipped past a critical point. There is now more carbon than oxygen in its atmosphere. This means that as the gas cools in the star's expansive outer layers, the carbon atoms are free to link together, forming tiny particles of graphite and silicon carbide, essentially soot. This soot condenses into microscopic dust grains right there in the star's atmosphere. The star's immense gravity can no longer hold onto these dense dust grains. They are pushed outward by the intense radiation pressure from the star's brilliant core, much like ash is carried upward by the heat from a fire. As the dust drifts outward, it forms a thick, opaque shell that blocks the star's visible light. But this shell is not cold. It is warmed by the starlight it absorbs, and it re-radiates that energy as a torrent of infrared radiation, creating the incredible glow we observe. The star is literally enveloped in a warm, cosmic cocoon of its own making. What makes this star in the Mice Galaxies so extraordinary is the sheer scale of this process. The rate at which it is ejecting this carbon-rich material is orders of magnitude greater than what we see in isolated carbon stars. It is in a state of hyper-evolution, and the trigger for this premature and violent retirement appears to be the galactic collision surrounding it. The merger environment is the ultimate agitator, a cosmic catalyst that can accelerate stellar life cycles. The same shockwaves that compress gas to form new stars can also jostle and perturb the interior dynamics of older, evolved stars. One compelling theory is that as this star was orbiting through its galaxy, it passed through a particularly dense region of gas and dust compressed by a merger-induced shockwave. This sudden increase in external pressure could have physically squeezed the star's tenuous outer layers, destabilizing them and triggering a much more intense and accelerated episode of mass loss. It's akin to squeezing a tube of toothpaste. The external pressure forces the contents out far more violently than they would naturally ooze out on their own. Another fascinating possibility involves a stellar encounter. The gravitational frenzy of the merger has increased the probability of close passes between stars. It is conceivable that a rogue star or a dense stellar remnant passed unusually close to this red giant. The gravitational tug from this flyby could have exerted tidal forces on the giant, stirring its interior and disrupting its atmosphere. This stellar nudge could have shaken loose the delicate balance in its outer layers, kicking off the intense mass ejection we now witness. Furthermore, the simple act of the star being violently jerked around by the changing gravitational field of the merging galaxies could have the same effect, churning its insides and hastening its evolution. This carbon star is a stellar canary in a cosmic coal mine, its accelerated demise a direct and visible consequence of the environmental chaos. It shows us that a galactic merger doesn't just affect the birth of stars, it can also orchestrate and dramatically speed up their death, seeding the surrounding space with the heavy elements and dust that will one day form new planets and perhaps even the foundations for life elsewhere. And now we arrive at the most visually spectacular and iconic signature of the entire collision, a feature so beautiful it has become the defining portrait of the Mice Galaxies. Lining the immense arching tidal tails like diamonds sewn onto a cosmic ribbon is a breathtaking sequence of brilliant blue star clusters. This is the string of pearls, a direct and stunningly beautiful consequence of the gravitational violence that has reshaped these two galaxies. Each luminous pearl is not a single star, but a massive cluster containing thousands of newborn suns, their intense blue-white light signaling their incredible youth and ferocious energy. This is the hallmark of a galaxy merger, a universal fingerprint that tells us we are witnessing one of the most creative and destructive processes in the universe. The formation of this celestial jewelry is a story of chaos giving birth to order. When the two galaxies first interwove, their gravitational tides didn't just pull stars and gas out into long streams, they also created powerful shockwaves that raced through these ejected rivers of material. Think of it like flicking a long, taut rope. A wave travels down its length, and where that wave meets a kink or a knot, energy is concentrated. Within the tidal tails, these shockwaves compressed the vast clouds of primordial hydrogen gas which had been stretched thin across space. The immense pressure from these waves overcame the gas's internal pressure and turbulence, pushing countless atoms closer together. In specific regions along the tail, the density of the gas crossed a critical threshold. At that point, the relentless force of gravity took over from the shockwaves, and these local pockets of gas began to collapse catastrophically under their own weight. This collapse wasn't a single, uniform event. Within each collapsing cloud, smaller knots of even higher density began to form, fragmenting the giant cloud into hundreds of individual stellar nurseries. As these knots shrank, their cores heated up due to the increasing gravitational pressure until temperatures and pressures reached the millions of degrees necessary to ignite nuclear fusion. Almost simultaneously, across a volume of space dozens of light-years wide, thousands of new stars roared to life. The most massive of these new stars are absolute behemoths, burning their hydrogen fuel with a desperate intensity that makes them blaze with a surface temperature far hotter than our Sun. It is the brilliant blue-white light from these hot, massive stars that dominates the glow of each cluster, making them stand out so vividly against the darker, redder background of older stars. The string itself, the reason these pearls are lined up so perfectly, is a direct record of the shockwave's journey. The wave didn't compress the entire tail at once. It moved through it, triggering star formation in a sequential manner. The clusters we see today mark the points of peak density within the tail, the places where the gas was already clumped just enough for the shockwave to push it over the edge into collapse. The relative ages of the clusters can even be traced along the tail, with the youngest pearls typically found nearer to the galactic bodies where interactions are still ongoing, and slightly older clusters located farther out, showing where the wave passed through earlier in the collision process. This isn't a static picture, it's a frozen movie reel of the star formation trigger propagating through intergalactic space. This process is the universe's ultimate example of recycling on a grand scale. The gas that now forms these brilliant new stars was once the raw material for previous generations of stars within the tranquil spiral disks. It was forged in the hearts of those stars, enriched with heavier elements, and then expelled back into space through stellar winds and supernova explosions. The galactic merger then scooped up this recycled material, flung it into the darkness, and through an act of incredible violence, provided the conditions for it to collapse and form a new generation of stars. The string of pearls is more than just a pretty picture. It is a living laboratory that demonstrates how the largest scale gravitational dynamics in the universe directly govern the smallest scale process of star birth, weaving together the physics of the cosmos from the largest scales to the smallest in one magnificent glowing chain. From misaligned black holes firing chaotic jets of energy to the silent, gravitational pull of invisible dark matter clumps, from hypervelocity stars rocketing into the void to the delicate crystalline structure of cosmic dust forged in shockwaves, the Mice Galaxies are not just a pair of colliding spirals. They are a comprehensive cosmic laboratory, a single system where we can observe nearly every extreme and bizarre phenomenon the universe has to offer. This one ongoing event contains stellar nurseries of unbelievable scale, the ghosts of long-devoured dwarf galaxies, enigmatic objects shining with impossible power, and magnetic fields woven into ordered patterns across thousands of light years. It is a place where stars are born in solitude and die in spectacular isolation, where entire new galaxies may be struggling to form from the debris, and where the very fabric of space-time is rhythmically pulsed by the dance of supermassive black holes. What this incredible menagerie of strange objects ultimately tells us is that the life of a galaxy is anything but serene. It is a dynamic, violent, and continuous cycle of destruction and creation, where chaos is the primary architect of beauty. Galaxies are not immutable islands in the void. They grow, they collide, they merge, and in doing so, they trigger bursts of new life while simultaneously preserving fossils of their deepest past. The Mice Galaxies are a snapshot of this grand evolutionary process, demonstrating that from the most colossal collisions come the ingredients for new worlds, new stars, and the very elements that make life possible. It is a powerful reminder that we are the products of such cosmic violence, born from the debris of ancient explosions and mergers that occurred long before our Sun even ignited. We want to hear which of these strange objects captured your imagination the most. Was it the runaway hypervelocity star forever exiled into the darkness? The mysterious dark matter clump that shouldn't exist, or the cosmic gem factory creating crystals on an interstellar scale? Let us know in the comments below. Share your favorite cosmic mystery from this journey. If you enjoyed exploring the beautiful chaos of the universe with us, make sure to subscribe and hit the notification bell so you don't miss our next voyage into the depths of space, where we'll continue to unravel the wonders and weirdness that lie hidden in the